When you're a jet all the way from your first cigarette to your last dying day. When you're a jet, if the...
In this video, we'll focus on examples of the construction that we talked about in the first video and in the last lecture. So the first thing we want to do is take the example where f is the real numbers and our irreducible polynomial is x squared plus 1. This doesn't have any roots in R. This is irreducible in R bracket x. So if you take the quotient of R bracket x by this ideal generated by x squared plus 1, you get a field K. This has a subfield isomorphic to R. And the degree of this extension is the degree of this irreducible polynomial is 2. And P of x has a root in K. So we know now what the elements in K look like. One way to represent them is as polynomials in theta, where the degree is at most n minus 1, so the degree is at most 1. And theta squared plus 1 equals 0 in K. Theta is a root of P of x in K. And just moving this to the other side, that means theta squared equals minus 1 in K. We know how to add elements. We add a plus b theta plus c plus d theta is just a plus c plus b plus d times theta. And we know how to multiply now, where we take a plus b theta times c plus d theta is ac plus bd theta squared plus ad plus bc theta. And now we just want to use this observation that theta squared equals minus 1. And that gives us ac minus bd plus ad plus bc times theta. So we're getting the product of these two polynomials of degree at most 1 as a polynomial of degree at most 1. And now if you look at this addition rule and multiplication rule, you might notice that this looks exactly how you add or multiply elements a plus bi and c plus di in the complex numbers. We really think of I as being this complex number, square root of minus 1. And this is not a coincidence. These fields, K and C, are isomorphic. So if you consider the map that takes an element in K, what does that look like? Well, it's a coset of x squared, the ideal generated by x squared plus 1 in R bracket x. It's represented by a polynomial of degree at most 1. So you take an element in here, a plus bx, and you send it to a plus bi. So the defining thing here is that everywhere you see an x, you put in an I, square root of minus 1. This is a homomorphism of rings. These are both fields. It's a ring homomorphism. That's easy to check. I'll leave the details to you. It's also a bijection. So it's a bijection. For example, you could think of each side here as being a two-dimensional vector space over R, and now it's clear that it's a bijection of vector spaces. So it's a ring homomorphism that's injective and surjective. It is an isomorphism. So it's an isomorphism of rings and also of fields. So what are we seeing? We started with R bracket x and this irreducible polynomial of degree 2. And we constructed a field that was isomorphic to C. So as long as you're comfortable identifying a field with a field isomorphic to it, you could use this as a definition of the complex numbers. So you can define C not in terms of this special element in the complex plane I that squares to minus 1, but as this degree 2 extension of R. All right, so this is going to be a big theme throughout the rest of the course, thinking of fields being constructed in terms of quotients by irreducible polynomials, adjoining roots of polynomials, things like that. All right, so we could do the same example exactly, but instead of starting with f equals r, we'd start with f equals q. So we'll take the same polynomial, x squared plus 1, irreducible still. We get this quotient, and we can think of the elements as a plus b theta, where a and b are now in q, and theta squared plus 1 equals 0 in k. And if you do the corresponding thing where you take elements of k, say a plus b theta, and send them to a plus b I, now we get an isomorphism between K and this field Q adjoin I that we saw at the beginning of chapter 7 of Dominant Foot. Okay, so I'm going to pause and erase, and I'll talk about more examples. And then also I'll return to this question that we talked about at the end of the last video about how to find the inverse of an element in K. Let's discuss some additional examples. We could take f equals q and our irreducible polynomial to be x squared minus 2. This is irreducible. It doesn't have any roots in q. Let's take k then to be the field that we get by taking the quotient by the ideal generated by p of x. And we know that we can represent elements as a plus b theta, where a and b are elements in q, and theta squared minus 2 equals 0, which means that theta squared equals 2 in k. So what is k? K is a degree 2 extension of q in which x squared minus 2 has a root. What's a root of x squared minus 2? It's a square root of q. So I'm using this a little informally right now. We can use this symbol, square root of 2, in place of theta. Because what is theta? It's some element in k in which for which theta squared equals 2. So if you put in this symbol everywhere that you would see a theta, then how do you multiply? Well, a plus b root 2 times c plus d root 2 is ac plus bd square root of 2 squared plus ad plus bc square root of 2. And that is ac plus 2bd plus ad plus bc square root of 2. And why is that true? This is theta squared, which we know is 2. So we replace this square root of 2 squared with an actual rational number 2. Okay, so we can see, doing the same thing that we did in the last examples, that we can actually give an isomorphism between k and the field q adjoins square root of 2, which is an example of a quadratic field that we've talked about in Math 206b. All right, so let's take a polynomial of slightly higher degree. Let's look at an example where f equals q and p of x is x cubed minus 2. This is irreducible. It still doesn't have any roots. It's also irreducible because it's Eisenstein at p equals 2. So you take this field given by the quotient by this ideal, and you get k, which we can represent elements as a plus b theta plus c theta squared. A, b, and c run through q, and theta cubed equals 2. This is a degree 3 extension, and k has a cube root of 2. So there's a solution to x cubed minus 2 equals 0. Okay, so let's talk about inverses of elements. We know that theta times theta squared equals 2. So that means, what is the inverse of theta? Well, take square root of 2 and divide by 2, and you get 1/2 theta squared is theta inverse in k. So we know how to find the inverse of the element theta. But what about other polynomials of degree at most 2? So in Dummett and Foote, they give you the inverse of theta plus 1. I'm going to talk about the same issue, but use a different example. What is the inverse of theta squared plus 1 in k? So here's the big idea. By the Euclidean algorithm in q bracket x, right here, k is defined as this quotient of q bracket x. There are polynomials a of x and b of x in q bracket x such that a of x times x squared plus 1 plus b of x times x cubed minus 2 equals 1. Why is that true? Because the GCD of these two polynomials, x squared plus 1 and x cubed minus 2, is 1. All right, so now it's clear that if you take the quotient by the ideal generated by x cubed minus 2, this term goes away because this polynomial is in the ideal generated by x cubed minus 2. And applying the projection homomorphism, a of x times x squared plus 1 gets sent to a of theta times theta squared plus 1, which is also 1 gets sent to 1. This equals 1 in k. So a of theta is theta squared plus 1 inverse in k. And if you think about how the Euclidean algorithm works, we can choose a of theta to have degree at most 2. All right, so now it's an exercise to find a of x and b of x, by which I mean we already know how to do this. We know how to do the Euclidean algorithm, but we haven't done it in a long time. So one thing I'll point out is that on the Math 206B final exam, there was a case where you had to find the GCD of two polynomials by applying the Euclidean algorithm. Originally, that problem had come from an exam where that was the first part. And the second part was to find polynomials a of x and b of x such that a of x times your first polynomial plus b of x times your second polynomial was equal to the GCD. So I didn't make you do that on the exam because it just involved a bunch of arithmetic that I thought was not great for stressful timed exam. So I'm going to pause and erase, and I'll actually do this example and really show you like what is a of theta that is theta squared plus 1 inverse in this field K. Let's do the details of this example where we're trying to find the inverse of theta squared plus 1 in this field K that is q bracket x mod the ideal generated by x cubed minus 2. Okay, so we know what we have to do is use the Euclidean algorithm in q bracket x to find polynomials a of x and b of x such that a of x times x squared plus 1 plus b of x times x cubed minus 2 equals 1. So how do we do that? First, let's divide the higher degree of this by the next one. So x cubed minus 2 by x squared plus 1. And we see that x cubed minus 2 equals x times x squared plus 1 minus x plus 2. So now we're going to divide x squared plus 1 by this remainder, negative x plus 2. There are some minus signs that cancel here in an annoying way, but x squared plus 1 is negative x minus 2 times negative x plus 2 plus 5. So what is it? It's x minus 2 times x plus 2, which is x squared minus 4 plus 5. So what does that mean? Let's now rewrite this, isolating 5, which is a unit in q bracket x. So 5 is 1 times x squared plus 1 minus x minus 2 times x plus 2. And we know that we can write minus x plus 2 in terms of x cubed minus 2 and x squared plus 1. So let's do that. So 5 equals 1 times x squared plus 1 plus x minus 2 times 1 times x cubed minus 2 minus x times x squared plus 1. And now let's group together the things, the factor of x squared plus 1 and the factor of x cubed minus 2. And what we see is that 5 equals something times x squared plus 1 plus something times x cubed minus 2. So let's see if I did this arithmetic correctly. 1 times x squared plus 1 plus x minus 2 times minus x times x squared plus 1. So it should be minus x squared plus 2x plus 1 times x squared plus 1, and then plus x minus 2 times x cubed minus 2. Okay, so now we found 5 as a polynomial linear combination of x squared plus 1 and x cubed minus 2. How do we go from 5 to 1? We'll just divide by 5 everywhere and see that 1 equals 1/5 times this thing times x squared plus 1 plus 1/5 times x minus 2 times x cubed minus 2. So now going through this process we described here, 1/5 times minus theta squared plus 2 theta plus 1 is theta squared plus 1 inverse in K. And you really can check that if you take the product of these two things, you get 1 in K. Meaning that you get 1 plus some, if you replace these thetas now again by x's, you get 1 plus some polynomial that's divisible by x cubed minus 2. Okay, so in general, what do you do? This is one polynomial in one field. But in general, if you have this field that's given by f bracket x, where f is a field mod the ideal generated by p of x, an irreducible polynomial of degree n, let's say, and you have f of theta, a polynomial in theta of degree at most n minus 1, so an element of K, how do you find f of theta inverse? You apply the Euclidean algorithm to produce two polynomials, a of x and b of x, in f bracket x, such that a of x times f of x plus b of x times p of x equals 1 in f bracket x. And if f of theta is a non-zero polynomial of degree at most n minus 1, that means that f of x and p of x, this irreducible polynomial, are relatively prime in f bracket x. So you can do this. And then what is f of theta inverse? What is the inverse of the element f of theta in Q? It's this a of theta, which comes from this polynomial a of x. And because of how the Euclidean algorithm works, a of theta can be taken to be a polynomial of degree at most n-1 in K. All right, so I'll pause and erase, and I'll talk about another kind of example. Let's next look at an example with finite fields. So let's let f be the finite field of two elements, and p of x be x squared plus x plus 1. This is an irreducible polynomial in f2 bracket x. How do you check that? Well, it has no roots in f2. 0 is not a root, 1 is not a root, and there's nothing else to check. So what that means is that K, f2 bracket x, mod the ideal generated by this irreducible polynomial, is a degree 2 extension of f2. It contains a subfield isomorphic to f2. And it is a finite field of size 4. So it's a vector space of dimension 2 over f2, so it has 4 elements. And how can we think of the elements of K? We can think of them as a plus b theta, where a and b are elements of f2. So since there's only 2 elements of f2, we can just write these down. These are the 4 elements, 0, 1, theta, and 1 plus theta. And what's true about theta? Theta squared plus theta plus 1 is 0 in K. So we know how to add and multiply in K. How do we add? Well, I've taught Math 120A, the intro group theory class, a number of times. You can write down this convenient little group table for your finite group to just keep track of what happens when you add the thing in this column to the thing in this row. That gives you each entry of the table. And adding 0 just gives you the first column along the top. Adding 0 over here gives you first row, or gives you the rows in order. This is clearly symmetric because plus is abelian. You add any element to itself, you're in a field of characteristic 2, you get 0. Like 1 plus theta plus 1 plus theta is 2 plus 2 theta. But 2 times 1 and 2 times theta are both 0 in this field of characteristic 2. And you can check the other entries here. How do you multiply? Maybe it's more interesting. You can do the same thing where you write down a table, multiply anything by 0, you get 0. This is clearly symmetric because multiplication is commutative. Multiply by 1, you just get, that's the identity, you get back the element. Theta squared is 1 plus theta, because theta squared plus theta plus 1 equals 0. Theta squared is minus theta minus 1. But minus theta minus 1 is theta plus 1 in a field of characteristic 2. And you can check, like 1 plus theta times 1 plus theta is theta squared plus 2 theta plus 1. But theta squared plus theta plus 1 is 0. So that just is theta. So this should look familiar. We know that additively, a finite field of order p to the n is isomorphic to z mod pz cross z mod pz cross 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 n times. Here we're just seeing exactly this in the case that n equals p equals 2. And here, okay, if you multiply by 0, you just get a bunch of zeros. But if you look at the non-zero elements, so take the bottom right 3 by 3 corner of this table, what you're getting is the group table for the units k star under multiplication. And this looks just like the group table for z mod 3z. I mean, it has to. There's only one group of order 3. But this is also just showing us in one very concrete example that the multiplicative group of a finite field that's not z mod pz, a finite field of prime power order that's not of prime order, is cyclic. So this is cyclic with generator either theta or 1 plus theta are both generators for this group. Okay, so let's talk a little bit more about getting finite fields through this kind of process. We didn't have a whole lot of choice here. There's only one irreducible polynomial of degree 2, monic irreducible polynomial of degree 2 in f2 bracket x. You can just count. I mean, there's only 4 of these polynomials, and the other ones either have a root at 0 or a root at 1 or both. So what about if you take f equals f3 and you take the two different polynomials of degree 2, p1 being equal to x squared plus 1, and p2 being equal to x squared plus 2x plus 1. These are both irreducible in F3 bracket x. Neither one has any roots. You plug in 0, you plug in 1, you plug in 2, plug in 0, plug in 1, plug in 2. So that means that K1, the field you get from F3 bracket x, mod the ideal generated by x squared plus 1, and K2, F3 bracket x, mod the ideal generated by x squared plus 2x plus 2. Each one of these is a finite field of order 9, because each one is a field that is a vector space of dimension 2 over F3. So what do we know about K1? It's an extension of F3 of degree 2 in which x squared plus 1 has a root. And what do we know about K2? It's an extension of F3 of degree 2 in which x squared plus 2x plus 2 has a root. But if you look at this polynomial, x squared plus 2x plus 2, this also has a root in K1. K1 is constructed to have a root of x squared plus 1, but it also has a root of this other irreducible polynomial. How do we know? You just find one. So playing around with this, if you plug in 2 theta plus 2 or minus theta minus 1, I think is a little easier. Squared plus 2 times minus theta minus 1 plus 2. What do you get? Well, the minus cancels out here. You get theta squared plus 2 theta plus 1. This is 2 times theta. Yeah, this is 2 is minus 1. So you take 2 times minus theta minus 1. And what you get is theta plus 1 plus 2. Now we have 2 theta plus theta, which is 0 in F3 bracket x. And then 1 plus 2 is 3, which is 0 in F3 bracket x. So it's also 0 in K1. And now what we're left with is theta squared plus 1, which in K1, that is 0. Theta squared plus 1 equals 0 in K1. So we found a root of this other irreducible quadratic polynomial in the first field. And if you can do the same thing to see that P1 of x has a root in K2 also. So the question is, how are these fields, K1 and K2, related to each other? So each one of them came from taking the quotient of F3 bracket x by some irreducible polynomial of degree 2. It turns out these fields are isomorphic to each other. You can try to write down an isomorphism between them. And more generally, what we'll see much later in the course is that all finite fields of order p to the n are isomorphic to each other. You can describe them all as Fp bracket x mod the ideal generated by some irreducible polynomial of degree n. And part of what this is saying is it doesn't matter which irreducible polynomial of degree n you take. Whichever one you take, you get an isomorphic field. Okay, so I'll pause and erase, and I'll finish this video with one additional example of a slightly different kind. First, I've written a reference up at the top here in case you want to look ahead and see this result that all finite fields of order p to the n are isomorphic to each other. This is proposition 15 in section 14.3 on finite fields and Galois theory. I want to end this video with one other type of example. Let's let F be K adjoin T, the field of rational functions in T over the field K. And let's consider P of x to be equal to x squared minus T, which is a polynomial in F bracket x, which, okay, what is F? This is K adjoin T bracket x. This is an irreducible polynomial, but we haven't thought about this kind of example in a little while, so let's explain why that's true. This polynomial is irreducible in K bracket T adjoin x. Why is that? The ideal generated by T is prime in K bracket T because you take the quotient of that ideal and what you get is K, which is an integral domain. So it's a prime ideal. So this means if you look at the coefficients of this polynomial, each coefficient, it's a monic polynomial where each coefficient is in the ideal generated by T, and the constant coefficient is not in the square of that ideal. So P of x is irreducible because it's Eisenstein at T. And now, because it's irreducible in K bracket T adjoin X, by corollary 6 in section 9.3, this is this corollary to Gauss's lemma, P of X is irreducible in F bracket X as well. In this field of rational functions, K adjoin T bracket X, K adjoin T, this field of rational functions, is the field of fractions of K bracket T. Okay, so we're using the Eisenstein irreducibility criterion in a setting other than a polynomial with coefficients in Z here. All right, so now we can take K to be the field that is F bracket X mod the ideal generated by P of X, and the elements look like A of T plus B of T times theta, where A of T and B of T are in this field of rational functions, K adjoin T. And what's true about, just really for emphasis, the coefficients in these rational functions, in the polynomials giving these rational functions, are in this field K, little k. So this is capital K, this is little k. So I wanted to bring up this example because this kind of example will be useful when we talk about some of the unusual things that can happen with fields later on in the course.